Does it record? I guess it tells you. Okay, so yeah, thanks again for the invitation for IICCSSS. Not so hard, it's not so easy to Google, but it sounds like a really cool conference. I'm happy that cognitive science seems to be kicking off more and more in Germany, but also, like Central Europe more generally. That's quite nice. There seem to be a bunch of really interesting people who have just moved to Germany or have been here for a while. It's really nice to see how these things come together. And yeah, it's also a bit sad that this is not actually in Tübingen, because I'm presenting to you from Tübingen, where I have this lab working on computational principles of intelligence. And I'm going to try and talk to you a little bit about some of these sort of principles that I think might be important if you want to build an intelligent agent. And humans are, by our definition, intelligent agents most of the time. And you will see that, like, having found these principles, I want then to apply these principles to a bunch of different domains. And that is sort of the research agenda of the lab, the overarching theme. And my apologies already, some of you might have already seen some of the stuff, Timo and Leonie, for example, but for sure also Toby. Okay, let's start right away. So I did a postdoc in Boston. When I moved there and I went to the supermarket for the very first time, I wanted to buy yogurt. Unfortunately, or maybe for the better, the sort of yogurt distribution in the US looks a bit like this. You have thousands of different brands. You could now really, if you behaved like what neuroscience thinks humans behave, sample each of these options individually, build up a representation of which of these yogurts you like the most, and then keep sampling that yogurt, right? Of course, as a postdoc, you have only a limited time, and you for sure only have a limited budget. So you should probably use some other information to speed up the way that you explore this space. One such information, for example, could be the actual spatial distribution. So for example, if you're on a postdoc budget, you might sample down here because that's where it's normally quite cheap. Okay, so this brings me to this general idea of, okay, how can we model exploration exploitation in these more realistic types of setups? Many psychological and neuroscientific studies use these two-armed bandits. I always thought they were kind of interesting, but not at all plausible if you go into the real world. So I want models that can really get some traction on modeling behavior in the actual wild. So the exploration exploitation dilemma, just for the people who did not know about this, is sort of this trade-off of, should you explore something new to maybe find out some information, like the grand opening of a new restaurant, or should you go to the usual place, Sternwarte, for example, here up here on the hill, and just go for what you know and maybe enjoy that. Okay, but there's this problem, as I have shown to you with these yogurts, right? That in these vast problem spaces, how could we or any other agent learn which actions to select when not all outcomes can ever be observed, right? I for sure cannot sample all the restaurants in Baden-Württemberg. I cannot even sample all the restaurants in Tübingen. So I have to use some other mechanisms, some other features to guide my exploration to eventually find something that I like. Okay. So this brings me to this one key principle that has been studied very widely in psychology called generalization. I mean, also very important in machine learning, of course, and in neuroscience. Interestingly, already Tolman, in his famous cognitive map paper, said that at last I come to the humanly significant and exciting problem, namely, what are the conditions which favor narrow or broad maps? So what are the conditions that have to be necessary, are required for animals to build these broad generalizing maps versus narrow maps? Sort of like 40 years later, Shepard wrote this really beautiful paper. It's a science paper on the general law of generalization, a universal law, where he shows that there is this exponential gradient that seems to be permeating through all of psychology and through all of domains. And he really thought that because any object or situation experienced by an individual is unlikely to recur in exactly the same form, psychology's first general law should be a law of generalization. And it's interesting how, like, this was 40 years later, and then 30 years later again, my postdoc supervisor and Nathaniel Doll, so in year 2 neuroscientists, wrote a paper where they said, because so in reinforcement learning, the data are relatively sparse, and indeed precisely the same situation may never be encountered twice. That's sort of opens up a huge problem for most reinforcement learning models that we use in psychology and neuroscience, because they cannot cope with these scenarios. So I want to build models that explore like people do and that use generalization to guide their exploration and that capture human behavior at scale. Okay, so one model that I quite like is a Gaussian process. I have used that model a lot throughout my PhD and postdoc, and actually Toby is still using this model in his project right now. Unfortunately, this animation doesn't work because I couldn't install Adobe on my Ubuntu so far. But a Gaussian process is basically a non-parametric Bayesian way to learn any stationary function. And all that you have to remember is that the Gaussian process is fully determined by this kernel function. And for a kernel function, for example, you could use a radial basis function, where you would just assume that the similarity of two options increases as these two options become closer in feature space. It's basically not saying nothing else than objects that are similar to each other are expected to produce similar rewards, for example. And I think that's quite a powerful mechanism because that captures something very quintessential about what psychology has thought generalization is like. For example, in this paper by Shepard, he showed that the probability to respond to a stimulus with the very same response decreases as an exponential function with the distance of that stimulus to another stimulus in some feature space. Funny enough, already Pavlov actually realized this and writes about this in his seminal work because he said that his dogs would not only react to the sound of a bell, but also to high-pitched voices in the lab, and would also produce saliva. So he thought already that maybe generalization could be at play here. And this kernel, the radial basis function kernel, actually assumes something very similar, where the correlation between two options rewards decays exponentially as the distance in feature space increases. It is basically a Bayesian formalization of this type of principle. Okay, but this still doesn't really tell us how to explore exploit, right? It would just, given some observations and some features, it would tell us what you would expect of kind of rewards for a new option. But how do you decide, like, what policy would you use to explore and exploit? And for this, one sort of strategy that I have used quite a lot is upper confidence bound sampling. Upper confidence bound sampling literally just adds the mean reward plus the standard deviation of a point of that reward together and samples the option with the highest upper confidence bound. It's a heuristic that actually has proven sublinear regret when combined with these Gaussian processes. And if you think about it, it makes sense, right? If you want to explore and exploit, the mean is sort of like the exploitation and the uncertainty is the exploration part. And Tom Griffiths actually in his paper, Algorithms to Live By, puts this quite nicely, where he says that if you encounter someone new at a party and you have never seen them before, treat them just like they are a bit better than the average person you know. Right. And this here is always when I say that you should also do this with talks from people whose talks you have never seen before. Okay, so for example, if the animations don't work. So if you put all of these together, you sort of have a generalization gradient that can be defined by this lambda. So the higher lambda, the higher this gradient, so the broader the generalization. This beta basically trades off between the uncertainty and the mean, so how much directedly someone explores. And then we also have a softmax temperature parameter that's just sort of like random value guided exploration. Put these models together, put these things together, and I think you have a powerful model that works over a bunch of different tasks. So one of the very first tasks that we did was this spatially correlated bandit. So this is work that back then Charlie Wu, a PhD student who's now also in Tübingen as a PI, has done. So we show people this grid. They can click on options and they get the reward of those options. So each tile is an option. However, there's a catch. There's actually an underlying correlation. So you can click on an option and nearby options will produce similar rewards. You can click on the same option multiple times. It will just have some noise always with some randomness. So if you were to behave like a normal reinforcement learning agent, like a Kalman filter or a Scholar-Wagner or what have you, then you would have to explore all of these options individually until eventually you might find something that is good and just stick to it. But if you actually use generalization, you can use the spatial locations or the x, y coordinates of these options to guide your exploration in this spatial field. So if people do this, then we would think that they would benefit from smooth environments where this correlation is stronger, more than from rough environments where this correlation is weaker. So we gave participants 20 trials per round, so much less than there are options here, and we gave them 8 rounds in total. You see that In smooth environments, they perform much, much better than in rough, but in both of these environments, they perform relatively well, needing only a few trials to already be quite good. What Charlie and I then did, and this was really work during the PhD over months and months, we basically came up with 4 times 6 plus 3 different models. So it was 27 different models, 4 learning models and 6 exploration strategies, 6 policies, and then 3 heuristics on top of that. And for each participant individually, we fitted these models to all but one block and then predicted their choices in the left out block. Doing this for all blocks over all participants then gives you a predictive loss over the whole set of participants. And we did 2 experiments. One was sort of 2D, one was 1D. In general, the finding is the same, that this GPUCB model, so the Gaussian process with upper confidence bound sampling, predicted most participants best. So this is sort of the total overview. Maybe let's zoom in a little bit. What you can see is that the Gaussian process predictive power is better than a mean tracker. A mean tracker is just a Kalman filter, so which can be redefined as some form of prediction error learning. There's some nice work on this, for example, by Nathaniel Daw. But also you need both the exploration and the exploitation parts together for this upper confidence bound sampling to really get some traction in predicting participants' choices well in this task. Okay, just briefly, we also had some work where, so one thing that we found that was quite interesting was the estimated lambda, so how much people generalized, was normally a bit lower than the actual true lambda of the environment. Then we thought, are people just stupid or is there something to it? So we did this massive simulation where we sampled the lambda from like we sampled environments from one lambda and then optimized these lambdas with another lambda. And we actually found that sort of slightly under estimating, slightly being pessimistic about the environment is a good thing to do for agents. So this actually led to a machine learning spin-off paper where we compared a bunch of different kernels and their smoothness assumptions in this optimization landscape. So we can also talk about this later. Okay. So now we sort of had this model, we wanted to apply it to some domains. One domain that we applied it to were kids. So there is this long-standing debate. So kids seem to sample in general more options than adults. Are they more random? Are they just like noisy? So some people like Alison Gopnik say that kids are more noisy and they are sort of simulated annealing is sometimes the metaphor that she uses, but you shouldn't take that metaphor too seriously. It's just like cooling down, so they get less random. There's another idea that maybe they generalize less and then they learn more about the world, they generalize more. Or there could even be that they sort of like basically explore more directly. So they really like seeking out uncertain options. So we did the same task, but with kids. We found one interesting thing already is that kids, for example, they rarely repeat choices. So this is the distance between consecutive choices. So 0 would be repetition. What you see is that adults really, they find the best option, they keep sampling it. Kids also, we made really damn sure that they know that they can repeat options, including multiple checks and so on. And most of them repeat choices as well, but they don't do it by far as much as adults. So they really like exploring around and opening these tiles. We then fitted a bunch of models. And basically the main finding was that generalization was higher for adults than for kids. And exploration, the directed exploration parameter was higher for kids than for adults. So you will probably critically, as you are, see that there are some values here close to 0. It doesn't really matter how you exclude them. If we do rank-wise comparisons, we did 20 different ways to compare these things, always the same result. Kids seem to explore more directly than adults, but there was no difference in random exploration. We did a bunch of recovery analysis here, like with all the models where we're trying to recover the parameters recover quite nicely. I even did this thing that I called counterfactual recovery. So I swapped the tau and beta, and I thought, okay, in a world where kids would differ in tau but not in beta from adults, would we have been able to find this? And yes, we would have been able to find this. So this was sort of like some interesting stuff we did there. We're now actually applying the same model in patients with depression. So because we think these parameters track something quite meaningfully, and we have a bunch of follow-up things, including Toby's cool work on letting these grids be generated and then assessing planning over these grids. Toby can tell you more about this, I'm sure, over the drinks later. But I said earlier on that I wanted to push these models to actual exploration outside of the lab. But this was still exploration inside the lab. It's just that we use 121 arms instead of 4 or 2, right? So what about exploration outside the lab? Well, many people always start with this restaurant example when it comes to exploration, exploitation, including myself. I just started with it. But no one really studies exploration, exploitation in restaurants. Up until this point, we studied it actually because Sam actually shared an office with this guy from Deliveroo. Deliveroo used to exist in Germany as well. Now they bankrupt in Germany, but they expanded into other places. So we got this data set of 1.6 million orders from 200,000 customers who basically over 2 months ordered on Deliveroo restaurants. And we got a bunch of features like what cuisine type it was it the first time they ordered from, and so on. And then we thought, okay, we can analyze this for signatures of exploration and generalization. And you will now see a bunch of plots. Each individually can be debated because this is noisy real-world data, but give me a chance to go to the end of it and you will see that I think a picture emerges. So one thing that we first wanted to see is, okay, if you take a restaurant's mean rating, so people see the mean rating of the restaurants on the side, right? It's the stars. And you subtract from that mean rating the average rating of restaurants of the same cuisine type in the same city. And their mean rating comparatively gets higher, then the people should be more likely to explore this restaurant. Right? It's just a sigmoidal choice function, as we normally see in neuroscience or psychology. Indeed, we find that the better the restaurant, the more likely are people to explore it. Now, there's this interesting prediction based on Sam's earlier work with two-arm bandits that if people actually do directed exploration, then a shift in relative uncertainty of an option, so increasing its relative uncertainty, should make people more likely to explore that option. So we got basically the relative variance. You can do the same thing with a relative standard error. It always comes to the same thing of that restaurant compared to all restaurants in the same city and same cuisine type. And then we did a median split. And what you see indeed is that there's a shift upwards in this choice curve. So people seem to like restaurants that have sort of a more variance in their ratings compared to restaurants that have a little bit less of this variance in their ratings. So maybe they give them sort of the benefits of the doubt. One question here comes up sometimes, can people even see all the ratings that people have given? Yes, they can actually click on it and they see the history of all the ratings. You can do the same with just price, right? So if a restaurant gets cheaper, people are more likely to explore that restaurant. And again, there's a shift upwards. This is highly counterintuitive because normally in economics, if you have two options, like two stocks, for example, you should actually be willing to pay a premium for the option that has less uncertainty. Sometimes this is actually used in pricing of options called risk uncertainty equivalent, where an option would be more expensive if it has less uncertainty. Here it seems to be the case because people might be exploring that they actually might be willing to pay more for a restaurant that has not been tried that often in the past. Okay. You can also see this with RPEs. So, if a restaurant, if they rated a restaurant better than the mean rating it had when they ordered from it, they're more likely to order from it again. So there's a thing to reward prediction error here. And again, there's a shift upwards for higher relative uncertainty. As a side note, one thing that I also tried back then was you can take these different cuisine types and you take whether or not the customer explored the cuisine type at time point t and try to predict whether or not he explored different or the same cuisine type at t+1. Note that exploration is defined as ordering from a restaurant for the first time. So this is not repeating the same restaurant. So you can get this matrix of how much does exploring one cuisine type predict exploring another or the same cuisine type in the next time point, and then cluster that correlation matrix. And you find some clusters that I think are quite, they make sense. Like there's sort of an Asian food cluster. There's a sort of like a healthy food cluster or hipster food cluster. The two things that are normally debated are German and Greek. People sometimes don't like that they come together. I call this pork. I'm vegetarian, so I don't like either of these food types so much. And then this thing I will label as unhealthy, burgers and American. Sometimes Americans don't like that label. You could also call it comfort food for reasons that I will tell you on the next slide. Because one thing that you can check is how likely is someone to explore from a cuisine type given certain experiences with a cuisine type on their last exploration. And what you then find is that in general, there's this like reinforcement effect, right? So if you tried the cuisine type and it turned out better than you expected, do more of it. There's also sort of a punishment reinforcement learning finding. If you tried the cuisine type and it was worse than expected, do less of it. Interestingly, the sign of these effects is actually, so if you take the signed effect, it's stronger for negative reward prediction errors. So people will be much less keen to try something again if it was worse than they would be keen to try something that was better than expected. This is especially pronounced for healthy food. And there's another trend, which is now why maybe unhealthy should be called comfort food. If people try from a restaurant and they have a bad experience, the most frequent switch that they do is to unhealthy in the next on the next time they explore. So maybe it's like comfort food, you know, burgers in America and something that you like. Now, probably some of you have doubted some of the stuff that I said about relative uncertainty and variance. So for those of you, I always wish that I could already get this too into your brain, because then I think you would doubt it less, because I think this is normally quite convincing. So what I did was I took a subset of these customers that is kind of maybe a weird subset. So they are like around 4,000 people who had just joined Deliveroo, and they really ordered, when they ordered, they rated every single order that they bought from, right? And we could actually track for each of the times that they went on the website, the restaurants that they saw and the features of that restaurant, like the price, average rating, how many customers have ordered from there before, and so on. And now we can actually use these features and try and make predictions about the restaurant that they will choose the next time they come on the website. And for that, we can again use different models. We can, for example, use just the mean tracker, so sort of like the classic Kalman filter. Clearly, this doesn't do anything because there are so many options. How would it ever get off the ground? We can use a Gaussian process that just generalizes but doesn't explore. It's already doing much better. This is out of sample prediction, always one step ahead. So I fit these models to all their choices up to time point t, and then I predict which restaurant are they going to order from at time point t plus 1. If we now combine the mean with the uncertainty to upper confidence bound, then we actually get quite a bit of traction. In fact, although I wasn't allowed fully to say this, but this model turned out to be better than the recommendation engine for some of the countries that they have on the website, which I thought was quite cool, because this means, you know, psychology is a thing that can be used in the real world to maybe make some meaningful predictions about what people will do. Okay, so this is sort of a transition from like the stuff that I have done during the PhD. I use these Gaussian processes in exploration tasks, in function learning tasks. I used them, sort of applied them to all sorts of different things. I went all crazy on them. Then in my postdoc, this was one of the projects that I did, was this Deliveroo project. And maybe now, like, because now I have students on my own, sort of I make some of them do this stuff, although the lab is moving on a bit past Gaussian processes. So it's not a one-trick pony lab. But one of the things that we've been working on recently is to see, okay, how can we port some of these insights on generalization into studies about the human brain, right? And I got lucky in collaborating with Christian Doller and Mona Garvert, and especially Mona Garvert then ended up designing this really beautiful experiment that I'm now going to tell you about. So I'm actually happy that I still have some time for it. So in this experiment, people explore in an arena. They sort of like walk around in an arena, and then they see some monsters. Over time, they learn the position of these monsters, and they're actually asked to recall them and so on. So see this here, like this is sort of the first person perspective. There are some landmarks. They learn where these monsters are. Then the next day, they come in, they again do this exploration task, but then they actually do an fMRI study where they always show two monsters, and people have to choose between these two monsters, and then they get a reward, and so on. So it's the two aren't banded, but the monsters change from trial to trial. And there's a catch, which I think is quite beautiful. The catch is that these monsters, their rewards are spatially correlated based on the location of the monsters in the arena, right? So basically, monsters, for example, in this context, monsters that were close like this. So these two guys, for example, they would both have high rewards. whereas monsters that were close here would both have no rewards. And it's sort of like a beautiful way to test some of these models that we had come up with, like the Gaussian process model. There were some other tasks, like she did some picture viewing tasks. This will become important because we sort of do a repetition suppression type analysis in a bit. And there were some left out monsters. So like there were some monsters that people never saw, but they experienced the rewards. And afterwards she asked them, can you position them? There were also monsters that people never experienced in the task, but afterwards she asked them, based on their position, what do you think would their rewards have been? She's a really great experimentalist, Mona, one of the best I've ever seen. So one of the first things that we sort of like, it's just did the experiment work basically? Well, in fact, you know, as the value of the right versus the left option increases, people are more likely to choose the right option. It's just, okay, do they get this at all? Yes, they do. Then she also asked them, so she had these inference objects and they had a high or low rating. And then she asked them after the task, they have never seen these objects in the bandit, but they know their position from the arena. What do you think is sort of the value of these options, right? And they do, she has 2 with high values and 2 with low values. And there's already an interesting thing that you can see, which comes back later. The high value options are a bit lower and the low value options are a bit higher than the values. This is actually a nice form of sort of like penalization towards the mean that actually the GP also does. Anyway, I'm really liking it. This plot is been a bit nasty because there's this one guy here, right? But I mean, we sort of like have been debating way too long about this one point. If you remove it, the correlation is still there. If you have it in there and you do a rank correlation, the correlation is there. If you do Pearson, it's there. Like it's, and in the end, we decided to keep this guy in, even though it's annoying because it creates a lot of white space. But this is sort of how well did they know the map, so the positioning task, and how much inference error did they do? And in general, the better they know the map, the less the inference error. Okay. So then for like 1 or 2 years, I was playing around with these with this data, and I tried different kernels and so on. It got some traction, so I got some sort of like performance of this model that I was trying. But then this new PhD student who Toby also knows, Tankred, came in, and he had this crazy idea that I think it's genius. So we saw that actually in the arena task, different participants explored the arena in completely different ways. So there were some people who sort of like went outside and occasionally inside. There were some people that we call the Germans. So like, you know, they sort of scanned, like, you know, they went like very, in a very rigid and organized way. And then there's some more people who maybe more like me, like they sort of stumble around, don't know what they're doing. And occasionally they go in the middle and then they find stuff. And Tankred had this idea that from their exploration behavior, one can actually create a kernel in the GP. So he does this by sort of the transition matrix of how likely are you, given what people do, how likely are they going to be to transition from this point to this point, from this point to this point. He uses the successor representation to capture this, but then kernelizes the successor representation into what we call a temporal representation. So this is like, what was the temporal sequence of the monsters that they had seen? And then what he finds is that the best model is actually one that has the temporal and the spatial component in generalization. So it is both their policy and the temporal dependencies of when they saw the monsters and the spatial rewards, the spatial positions of these monsters that are needed to explain this, to explain their choices quite well. And you know, you can see that, you know, like you can predict their inference errors quite nicely. The model recapitulates some of these errors and so on, but I guess you want to see some brain data. So Mona had these tasks where she found that in entorhinal regions, they track this dependency of cognitive maps. She does this by repetition suppression effects. And she actually does find an effect here. Unfortunately, it's an fMRI enhancement effect. There's loads of debate, including Chris Summerfield, where people don't seem to be very on one page what it means to be enhanced. But we find that with higher spatial weights in this kernel, there is actually an enhancement effect, or an fMRI spatial enhancement effect of these representations of the monsters in the entorhinal regions. And there's actually a nice overlap between these regions, between the spatial and the temporal prediction, and then the model that captures both of these. Maybe as a final thing, yeah, maybe this is quite nice. So wait, oh, I think I know this is here. So we also not only find that the kernel is a combined kernel of these two maps, the spatial map and the temporal map, but also because these rewards were generated by a spatial map, right? Actually, in hindsight, I wish that we would have found a condition that also gives people rewards based on the temporal structures that they experience, and we're working on this right now. But so what we see is that there's actually this interesting effect that if the prediction error of one map versus the other map in sign is higher, then you find a signal of evidence integration in OFC. And this is modulated, so in orbital frontal cortex. And this is modulated by the size of this effect. And this can also be related to the change in the map representation over time. So how much this changes over time is modulated by the signal in OFC that seems to be tracking some kind of weighted prediction error between these two maps. At least this is sort of where we're currently converging at. We still have to do a bunch of follow-up things, but this is where we're at the moment. So this is sort of, I wanted to show you a PhD project, postdoc project, now a PhD student of mine ongoing project. Okay, so in conclusion, I'm trying to create a theory of exploration and generalization that works across domains. It's based on 2 or 3 simple principles, right? Generalization is captured by kernels, exploration is directed by uncertainty. And I feel like if I had to bake a cake of intelligence, those would be 2 good principles to bake into this cake. Yeah, so I really think generalization and uncertainty are important to guide decision-making, big and small. We even have done studies in rats as well. So it's not only human animals that, that might be guided by this. And this Gaussian process upper confidence bound sample, I think, is just a beautiful model. It has all sorts of guarantees and relations to neural networks and so on. We can talk about this if you want. And yeah, currently we're working on representation learning in the brain. And maybe I should have added for you, Toby, we're also extending this to the planning domain where the GP is used as a model of the world. Yeah, so that's it. Thanks to you for the invitation. Thanks to my lab members, in particular, Mona and Tankred, who I added Tankred, I think, but maybe didn't compile. Tankred was really essential for the last part of this insight. And yeah, and then my 4 more postdoc labs as well. Thanks. Oh, and I forgot, Tankred is here. We're looking for a PhD student, so I think you're a good crowd to recruit from. I have funding to hire a PhD student that would be supervised by me, Jane Wang, and Matt Botvinnik to work on meta-reinforcement learning. So if you're interested, shoot me an email and we can talk about this. Thanks.